All right, so this is the last section in chapter 7. This is 7.4. And what's interesting about this section is that we're not going to construct a confidence interval. We're going to do kind of work in a little bit of a backwards direction. So there's this question that is actually what I like about this section is I feel like it's really applicable, right? So let's say you're a company and you want to report some mean or percentage within a certain margin of error, right? You know that you don't want to be too far off. Maybe you want to be within 0.01, maybe you want to be within 2 pounds or something, right? Whatever your problem you're working on. Your question is how many people do you need to sample, right, in order to get within that certain margin of error. So you're looking for an N in this chapter, asking yourself, how many samples do I need to take, right, in order to get in a certain margin of error, right? Because generally when you're doing studies and things, the cost becomes in how many people you have to sample or how many subjects you have to have or how many surveys you have to produce. And so if you can sort of learn or think about what your sample size needs to be, that can really help in sort of determining your cost, right? If I know I need to have 500 people to be within 0.01, then you know sort of how many people you need to have in order to have a certain margin of error, which is kind of what you're interested in as the researcher, is how much you're willing to kind of be within, right? Do you want to be really accurate or do you want to just sort of be slightly accurate, and how many people do you need to do those different things? So that's kind of the goal, is so your goal in this section is to find an N so that the margin of error is a certain amount. And so, in other words, E is given, but N is not. And your goal will be to find N. So there are two different things. Again, everything in this book is now sort of divided into two things, means and proportions. And so we're going to look at two different categories. We're going to look at means, and then we're going to look at proportions. And we're going to start with the mean section. So we'll start with that one first and talk about the formulas for that, where those formulas come from, and then how we'll use that in particular problems. All right, so for means, here we go. Let's look at this formula. So if you remember, the margin of error in a means for large means, and that's generally what we're working with here, is z of alpha over 2 sigma over n, square root of n, right? That's the E in our confidence interval formula. So it's not a new formula really, that's just the E part, right, of the x bar plus or minus E from the confidence interval section. I think that was 7.1 probably, or 7.2, probably 7.1. So now what we're going to do is we need to solve for n, right? And that will be our new formula for deciding on how to get n from all these other things that we know. So this is just really an algebra problem, and I'll work through this so you can kind of actually see where this formula comes from, so you know it's not just some random thing. So I think we're going to start by squaring both sides, right, because we've got to get rid of that square root. So if we square both sides, we're going to get e squared equals z alpha over 2 squared sigma squared over n. And then sort of getting n, we can sort of cross multiply here and take that over and take the other one down. We get n equals z squared alpha over 2 this is squared, sigma squared, and then divided by e squared. Right, just sort of cross multiplying these guys, e squared and n, and sort of switching those over. Right, and we get our answer here. So this is the formula we're going to use for means, is n is equal to z squared alpha over 2 sigma squared and e squared. And the big thing to note here is that we really need to know sigma in order to use this formula. And that's kind of going to be the crucial thing, is you have to have some idea about the population standard deviation in order for this formula to make sense. And the other big thing for this formula is always round up. All right, so always, always, always round up whenever you're using these formulas, because that's what it's all about. You always want to make sure you have enough. You don't want to go too low, right? Because you want to make sure you have this margin of error. So it's always better to be more cautious and round up by 1 than it is to round down. So no matter, even if it's 207.1, round that up to 208. Okay? We're going to look at the formula for proportions next, and then I think I'll work one of each so you can just kind of get a sense of how these problems work. And then we'll look at this quite a bit more in class on Wednesday. All right, so now we have proportions in a similar way. So if you remember the formula for proportions, it's the p hat, right, plus or minus z alpha over 2 square root of p hat 1 minus p hat over n. So this is your confidence interval formula, and again here E, right, your margin of error is z alpha over 2 p hat 1 minus p hat over n, right? And all that is under the square root. And again, we're going to try to solve for n. So we're going to square both sides. We get e squared equals z alpha over 2 squared. And then this just becomes p hat 1 minus p hat over n. And we want to get, again, n by itself. So then we just need to multiply both sides by n, and then divide both sides by e squared, right, to help get rid of e squared on that side. And if we do all of that, looks like we're going to get n equals z alpha over 2 squared, p hat, 1 minus p hat, all that's on top, and then it's going to be divided by e squared. So sorry, that formula is not the best. Okay, so we have all this in the numerator, z alpha over 2 squared, p hat 1 minus p hat, and that's all divided by e squared, and that's how we'll find n for problems that involve p hat. So this is all in the numerator, and then this is the one thing in the denominator. And so in doing this, again, here the thing you're supposed to know is p hat. And if you don't know p hat, the sort of best guess, right, the sort of middle ground, so if you have no idea about what p hat is, right, because that normally comes from our sample, and we haven't taken a sample yet. So it doesn't make sense necessarily we would know that going into the problem. But what we can know is either maybe some past statistic or something, and we can use that for p hat if that's given. Or if there's no information given about p hat, we can always use 0.5 because that's the most conservative estimate, in the sense that if we have anything smaller than that or bigger than that, then the 1 minus p hat will kind of cancel it out and we'll have a much smaller sample size. So 0.5 is kind of like the worst case scenario in terms of what this sort of final answer will be. So that's what we'll use as a conservative estimate. So if p hat is unknown, we're going to use p hat equals 0.5. Okay, so that's kind of that situation for that one. Okay, so that's proportions and means, and those are the two different categories that we'll look at, and we'll look at 2 examples, one for each. Alright, so let's try some examples. First we'll do one with means, and I think I'll look at number 21 in the book, which is similar to problem number 22, and it kind of takes a different direction, and I think makes it feel more applicable in my mind as to what you can do with it. So 21 says, you wish to estimate the current mean birth weight of all newborns in a certain region to within 1 ounce, or 1/16 of a pound, and with 95% confidence. So first let's write that down. We want to estimate the current mean weight to within 1 ounce or 1/16 of a pound. And if you notice the rest of the problem, everything else is written in pounds. So you want to take the pounds, not the ounces, and with 95% confidence. Okay, so those are the first 2 pieces that we need. And then a sample will cost $400 plus $1.50 for each newborn that we actually weigh. So that's the $1.50 times n, however many we end up sampling. And I believe, or you believe, that the standard deviation of weight to be no more than 1.25 pounds. So we can just use that, right, as our sigma, because we know it's not going to be any larger than that. And we have, we can spend $2,500. And the question asks us, can we afford the sample? And then after we do that, the question is, if not, what can we do? Okay, so this is a nice problem. I like it because it really sort of applies really what you're doing, right? In the world, sampling costs money, and generally you have so much money you can spend, and you have some conditions that you want, right? And in this problem, it has some conditions. We want to have 95% confidence. We want to be within 1/16 of a pound, and we know what the sample standard deviation, or the population standard deviation is, right? And we need to see, do we have enough money to do this, right, and get accurate results that we want? And if not, what could be some things we could change, right, in order to actually make this happen? So really quickly, before I leave this page, I think I'll write down the things that we have in terms of for our formula, right? So let's see, we know sigma is equal to 1.25. We know that E is 1/16, right, because that's what we want to be within. E is the error, right? So E stands for the error, so this is our error, right? That's the error that we want in order to be within a certain amount. And then last but not least, we also need z of alpha over 2, right? And in this case, this is z of 0.05 divided by 2, which is z of 0.025. And if you look that up in the chart, that's the 1.96 number. That's a number that you should almost have memorized at this point. The 95% confidence interval for z of 0.025 is 1.960. Okay, so we have all the values that we need to plug into our formula, and we can find n using that formula. So we'll do that on the next page. All right, here we go. So we have n, right, is equal to 1.96 squared, that's z of alpha over 2, times 1.25 squared, and then we divide that by our e squared, which is 1 over 16 squared. Right, that's that formula, z of alpha over 2 squared, sigma squared, and then over e squared. So, right, that's the formula for this section. All right, so once we do that, we can then calculate all that out. I got n is 1536.64. And remember, we always round up, so I'm going to say n is 1537. So that's the number I'm going to use moving forward. So if that's all that this problem had asked you for, was to calculate a sample size, you would be finished. You'd have n equals 1537, and that would be it. But this problem is interesting, right, that it has sort of a separate spot. So now you need to see how much it's going to cost you to run the survey. And remember, in the problem it says, originally you're going to spend $400 for the survey, regardless of how many people you have. And then you're going to spend $1.50 for each additional newborn that you have to weigh. And that we just got, we have to weigh 1,537 newborns. And so if you multiply all of that out, it looks like it's going to cost us $2,705.50. So we cannot afford this particular sample that's required in order to do the research to the conditions that we have so far in the problem. And so the question is, what can we do, right, to make this affordable, right? So right now, the standard deviation, right, the population standard deviation can't change. 1.25 is what it is, right? We have a error of 1/16, which we could change, right? But we're pretty confident that's the error we want, so I don't think you want to change your error. So the last thing in this formula, right, if you look at sort of the three pieces, right, we have a z, we have a sigma, and we have an e. These two things we usually don't want to change because those are the things that we're really, this we definitely cannot change. And then the e is really the sort of whole purpose of the problem, right? I want to be within this certain amount. So you can certainly change that if you think that's something that you're okay changing. But one thing that you definitely can change is your confidence level, right? This number right here. So if you have a smaller confidence interval level, then that number is going to go down. So you can always decrease your confidence level in order to get a smaller n. So that's what you can do. This is the answer to part B, right? You can always decrease your confidence level, and that gets you a smaller n, because that gives you, first of all, it gives you a smaller z, which of course then gets you a smaller n. Okay, so that's always one strategy. If you have a sigma that's set, you know that's set, you can't change it. You have a z that you really want, and maybe you just had too high of a confidence level in order to do the study that you wanted to do. So that's always an option in studies. If you have to change something, you can always change your confidence level. All right, so I'm going to work one more problem, this time on proportions. So this is problem 13 out of the book. And problem 13 says that the administration at a college wishes to estimate to within 2 percentage points the proportion of all its entering freshmen who graduate within 4 years with 90% confidence. We want to estimate the minimum size sample required. So we're just trying to find the sample size, and so again, we're going to use this formula n equals z alpha over 2 squared. This time it's talking about a proportion, right? So we're going to use the p hat 1 minus p hat over e squared formula in order to calculate n. Okay, so in this problem, we want to estimate to within 2 percentage points. So within 2 percentage points, so that's the first thing that we see in our problem that we'll need. And they want to do a 90% confidence interval. And that's pretty much all that's given. We want to find n. That's pretty much what the problem is asking. So within 2 percentage points, being very careful to convert that, that's our E, right? Within always tells you that's kind of your error. 2 percentage points is our 0.02, right? Being very careful about that. We want 90%, so that's Z of 0.1 divided by 2, which is Z of 0.05, which if we look that up in the table, I believe I got that to be 1.645. So you can look that up in the table to find Z of alpha over 2. And then the only other thing we don't have, right, so right now we're good. We have this guy, we have E. We don't know what this P is, right? And this problem didn't give us any information about P. So since we have no information about P, remember, we just use 0.5 as a conservative estimate. Okay, so that's the worst case scenario. So we're going to use that because that will, help us regardless of what everything else, what the real proportion is. So I think we now have everything we need. We now have a p hat number, we have a z, we have an e number, and we can just take all that and plug it into our formula to get n. So we're going to get n equals 1.645 squared 0.5, right, times 1 minus 0.5, and that's all divided by 0.02, be careful with a 0.02, squared. And if you plug all that in, work it all out, I got 1,691.2. And remember, all these problems you want to round up, so our answer here for n is 1,692. Right, that's our number regardless of what the decimal is. Always round up to be conservative. Make sure that you did take enough people to get the margin of error that you're interested in. So that's really all these problems are, is a straight formula calculation. Just make sure you use the right formula in the right situation. If you're talking about means, you're going to use the mean formula. If you're talking about proportions, you're going to use the proportions formula that we just used for this problem.